My group is not good at working during the weekends. So then we really start working on Monday.
Okay, so guys, what I'm sketching here is a normal distribution. Okay, so this represents a population, and I'm going to assume that the mean is equal to 80. I have to use my trackpad to write because unfortunately my tablet is acting weird. And I'm going to say the standard deviation is equal to 10. So that, since I use sigma and mu, which are parameters, that means I'm working with a population. If I had written X bar and SD for standard deviation, you would have known I'm talking about a sample. But this is the entire population. So we know from the empirical rule, from z-scores that we learned how to calculate, and so on and so forth, we know, for instance, that if this is really a normal distribution, that 95% of this population is between two standard deviations below the mean to two standard deviations above the mean, right? So we learned that about this normal distribution. We also learned one standard deviation below, one standard deviation above represents 68% of the population, and so on. So that was the empirical rule. That's a rough estimate for us, really. So, but it works for a truly normal distribution. It's not absolutely precise. So what we found was that when we had something that wasn't exactly two standard deviations below or two standard deviations above, we would then have to calculate how many standard deviations that is from the mean. So for instance, if I asked you what percentage of this population was under 65, let's say this is I don't know, blood sugar, right? What percentage of this population have blood sugar under 65? Well, 65 is about here somewhere, right?
The mean is 80 there?
The mean's 80, yeah.
Okay.
So 65, right? So 65, what is the z? How many standard deviations below the mean is 65? Well, we have a formula. Z is equal to, it's tough to write with this thing. Z is equal to the standard deviation of the population over the square root of the sample size, right? Okay, well, that's what I need to know for if I'm working with a sample, right? Because we have a sample size. We don't have a sample size here, we have a population. So with a population, the z-score is equal to the value that we're interested in, the 65, I'll put an X for it right now, minus the mean, mu, over the standard deviation, sigma. So in other words, if I asked you, what's the z-score for 60? Well, 60 is 20 below the mean. It's two standard deviations below the mean. So 60 is minus 2. The z-score is minus 2, right? But 65 is kind of an odd number. What's the z-score for 65? Well, 65 is going to be 65 minus 80 over 10, right? So 65 over, that's 15 over 10 is going to be equal to 1.5. So that's a z-score of 1.5. Is that a positive number or a negative number? Negative, right? Because for two reasons. Number one, because it's below the mean, right? So it's a negative z-score. And number two, because if you look at this, 60 minus 80, it's a negative number, negative 15 over 10, right? So that's a negative number. That also indicates that this number is smaller than the mean, which means it's to the left of the mean, right? So we're interested in finding this area in here, right? The area below 65. And we know the z-score is 1.5. So we can't use the empirical rule because it's not an even number, not one standard deviation, two standard deviations. So what are we gonna do about that? Well, we need a t-table, or we can use Excel, but for the moment, I'm gonna use the t-table. What did I do there in the background? Okay, I'm gonna get the t-table. Why did that come up?
Is that unusual for heater?
Yeah, and I have no idea how to work the thing. It's got this double touch thing and the soft touch and hard touch trackpad, and I'm always touching the wrong thing, and I can't find my desktop anywhere, except when I close everything. I can't figure out how to navigate to it. My 7-year-old MacBook Air was dying. The battery was completely shot. It was getting unreliable. It was full and slow, so it was time. I miss it though because I actually knew how to work the damn thing. So at any rate, you know, if you upgrade every few years, it's a small transition. If you wait 7 years to upgrade, it's a little bit of a bump. Okay.
The most nostalgic I've ever heard somebody get about a piece of electronic equipment.
What's that?
I'm very nostalgic about it.
Oh, well, yeah, I go way back. I go back to the Apple II before they had disk drives, when they used to load stuff off of tape, off of audio
I
tape.
remember that.
So, yeah, I go back there. I used to put together circuits, you ever see anybody wire wrap circuits? If I told somebody wire wrap, they have no clue what I'm talking about now. So at any rate, so negative 1.5. Do you have a background in technology, or is it a hobby?
Yeah, when I was very young, I was like into that. So.
Okay. So the C-score is negative 1.5. So now I got to go to my T-table, which somehow I wound up losing in this process. Okay, here we go. Okay, so let's take a look at our T-table. So if I'm looking for a Z-score of negative 1.5, I'm going to bring it up here so I can see it. Negative 1.50, in other words, negative 1.5 and no third digit, it's just a 0. It's going to be 0.0668. That means that the area to the right, notice how this is shaded, the area to the right of a Z-score of negative 1.5 is 6.68%. Did I get that right? Did I remember that correctly? 6.68%, right? So I'm going to go back to my chart. So this area represents 6.68%. Let me get that, my pen. Whoops, somehow or other I lost.
That will be under 65, is that right?
What's that?
Under 65 will be
From 65 down.
down, okay.
Right, 60 equal to 65 and down. Okay, and somehow my pointer my pen went away.
So that was a Z table or T table?
That's a Z table. Remember, we're going to get to the T table in a couple of weeks, right?
Okay.
That's a special kind of test where you compare means. But we're going to be working with that, right? So this is going to be 0.0665. Okay, so if I had asked you instead, what's the probability, what percentage of this population is above 65? What would you say?
You do 100 minus 0.0.
Exactly. It's what's left. In other words, if it's a proportion, it's 1 minus 0.065. If it's a percentage, it's 100 minus 6.65, right? And you'd find the difference. It'd be 90, approximately 90, 0.99335, right? So that would be percentages above there. If you wanted to find a percentage between two values, right? So for instance, maybe you wanted to know what's the percentage between 87 and 65. Here's 87. Oops. And here's 65. So 87, we can use the Z table only to find the area below the number we're interested in. So if I find the Z score for this, I can tell you what the area is from here down, right? But now I want to know the area, not from there for the whole normal distribution. I want to know the area only from here to that to 65. In other words, this area in here. Well, what I can do is I can look up this area from here down, that entire area on the Z table, and then subtract the 6.65% from that to get the area between these two values.
But just to be clear, the 6.65%, that's for the area 65 and
Under.
that,
And
a
under.
little bit at the end.
Yeah, which has a Z-score of negative 1.5.
Got it.
Right? Okay, so if I'm interested in the area between 65 and 87, I now have to calculate a Z-score for 87. So 87 minus 80 is over 10 is equal to 7 over 10, or 0.7. Positive or negative? Positive, right? Two reasons. One, we know because it's to the right of the mean, it's going to be positive Z-score. And number two, because the math comes out positive. 87 minus 80 is a positive number. So I'm going to go to the Z table and look up 0.0. So now I got to go to the second table, Whoops, I gotta get rid of the pointer. Okay, now I go to the second table because it represents all the values above 50%, right? In other words, positive z-scores. Okay, so the z-score for 0.070 is 75.8%, 0.758. Okay, so this is point, oops, 0.758. I apologize for using the trackpad. 0.7580, right? But my tablet's not. I don't want to reboot because I'm running out of power on this machine. I'm going to have to switch over to the other machine pretty soon. And I don't know if I can continue to record if I do that. So I want to get as much of this in as possible. So 0.7580. So what percentage of the population is between 65 and 87? Well, it's going to be 0.7580, which is the entire area to the left, less 0.065. If I take that away, I'm left with the area that I'm interested in. Okay, so I would subtract 0.06. So it's going to come out to be about 68%, right? Or 0.68, so on and so forth. I'm just going to estimate that. Okay, so that's basically how we deal with samples of how we deal with populations, not samples from populations. So now I'm going to take a new look now at situations where we are sampling from this same population. So if I have the same population again, okay, if we have the same population again, okay, and the mean is 80, and the standard deviation is equal to 10. This is our population. Now, if I take repeated samples of size 25, let's say, from this population, and I'm presuming I did this last week because I'm having, have a few sections now. Did we go over that last week? Did I ask you to use the random number table to pick out? Okay, good. Just wanted to make sure. Because I didn't want to have you guys staring at me and say, what is the guy talking about? We didn't do that last week. So at any rate, so we know if we take repeated samples of size 25 from this population over and over and over again, and each time we take a sample of size 25, we calculate the average for those 25, and then we accumulate all those averages and we draw a new distribution using only the averages. We know that the mean of all those those samples is going to be the same as the mean of the population, in other words, 80. But the standard deviation now, right? The standard deviation, I'm not going to call it sigma because it's not the population. The standard deviation of these sample means is going to be equal to the standard deviation of the population over the square root of the sample size. Okay, so in other words, it's going to be equal to 10 over the square root of 25 is 5. So it's going to be equal to 2. Okay, so what does that mean for me now? Well, let's think about this. That suggests to me that if I took sample after sample after sample after sample of size 25, that 95% of the samples in this population would be between 76 and 84. Right? Makes sense? Because why do I say that? Because it's still normally distributed. The sample distribution is normally distributed. So between those two numbers is 95% because there are two standard deviations below the mean and two standard deviations above for all of the numbers which are the sample means, repeated sample means. So that means if I take another sample, I'm 95% sure that the sample result is going to be between 76 and 80. 5% of the time, it's going to be either less than or more than 76 or more than 80, more than 84, right? Because that's just the way that they're falling. That's the way that this is working. So now I'm 95%, I have 95% confident that a new sample from this population is going to be between these two numbers. I'm going to work this, I'm going to turn this around a little bit. And I'm going to say instead that if I take a sample from this population, I'm not, half the time I'll get something under 80, half the time I'll get something over 80. Very occasionally I'll get exactly 80. I mean, it's just the nature of sampling. I might occasionally get an 80, but most of the time I'll be under or over. Usually I'll be pretty close to 80 though, right? So now if I get a number like 77, right? Yeah, let's say 77. Okay, so that comes up occasionally. That's probably not the most common result, but it comes up occasionally. It comes up more than 5% of the time because it's within that range of 76 to 84, within 2 standard deviations, above or below. Well, I'm going to turn this around a little bit, and I'm going to say to myself, I took one sample of sample size 25. I'm going to assume for now, for this week, we're going to assume that we know the standard deviation. We know what that is of the population, right? So I'm going to say, okay, 77, I know the population standard deviation is 10, right? So I know that this came from a population at a mean, that I don't know what the mean is, but I came from a population standard deviation 10. I know that. And I know my sample size was 25. So my standard deviation for my for my samples, for this sample, my standard deviation for the group that this came from is going to be 10 over the square root of 25 is going to be 2. That's going to be my standard deviation. So instead of looking at this as saying that's the actual mean, right? I'm going to say instead that let's assume that this is going to be a range for me. Now, since my standard deviation is equal to 2, I'm going to start out by saying, let's say the mean is close to that. However, I can't really be sure that the mean is 77 because I know I have a distribution of sample means that's going to have this amount of variability, this standard deviation. So instead, what I'm going to say is that the true mean, I think, is within 2 standard deviations of this number that I got on my one sample. That doesn't seem that outrageous, right? Because that's the way this behaves. 95% of my samples are going to be within 2. So maybe this one's within 2. So what is 2 standard deviations within this, from this number that I got? Well, 2 times the standard deviation for the sample means is 2 times 2 is 4. So in other words, I'm saying that since I got a result of 77, I think I'm 95% sure that the true mean is between, let's say 2 times 2 is 4, so is between 73 and 80. I'm sorry, 81, right? It's between 73 and 81. I'm 95% sure that that's true because the nature of this, since I know the standard deviation, nature is that 95% of the samples are going to be within 2 standard deviations of the real population mean. I may never know what the real population mean is, but now at least I have a mechanism for saying, well, I got a 77. I don't know if that's really the mean, but now based on the variability of the standard deviation that I got based on the population standard deviation, at least now I can say that I'm 95% sure the true population mean is between 73 and 81. Okay, so I can do this again. I can go do this. Maybe next time I'll get 81. Maybe the next time I'll get 80. And each time I do this, I can set up a confidence interval around the result that I got, basically doing the same thing. However, every once in a while, I may get a value. Let's say I may get a value like, maybe I'll get 75, right? So my confidence interval is 71. So I'm sorry. Yeah, 71 to 79. I'm 95% sure the true mean is between 71 and 79. What happened there? I'm wrong. It isn't there. What percentage of the time is this going to happen? 95% of the time I will capture the true population mean, right? In other words, I will get it so that the lower number and the bigger number have 80 between them. right? 95% of the time I'll get a,
Oh, 5%.
exactly,
Got it, okay.
I'm gonna be wrong 5% of the time. If I did this 100 times, how many times am I gonna be wrong?
5%.
5 times. I'll be right 95 times. So this is the trade-off. In other words, when we do a study, and someone maybe is measuring blood lead levels in children in the Bronx, comparing them to blood lead levels in children in, did I hit a nerve here? Is somebody doing research on that?
No, we were talking about another class today.
Oh, no, okay, what class?
Policy law.
Okay, good. So the action level now, I think is 5 micrograms per, 5 micrograms per deciliter of blood.
Yes.
Yeah, 5 micrograms per deciliter of blood. I do a demonstration with, I'll tell you about it later on. I'll tell you when I run out of power on the computer so I don't have to bore the people at home. So at any rate, so let's say somebody reports to you the average for children in this range in this neighborhood in the Bronx, based on our sample. They didn't test all the children. There might be 10,000 children school age in the Bronx. They tested a sample of 100 kids, random sample of 100 kids. So now they wind up reporting that the average for those 100 kids was 5.2 micrograms per deciliter. Well, that's very interesting, but it doesn't tell you anything about how accurate that number is. In other words, how close is that to the true mean for all 10,000 kids, not just the 100 that they sampled. But if they can give you a confidence interval, now you can say, oh, but we may not, in the sample of 100 students that we tested, the average was 5.2, but our 95% confidence interval suggests that the true mean is between 3.9 and say 6.2. Okay?
That means that would be statistically significant?
Well, that's a term we're going to use later on, not quite yet. All it tells us is that the result came up to be 5.2, but we're 95% certain that the true mean is between these two numbers. It's nice to know this number, right? But it's even nicer to know that we're 95% sure that it's between these two numbers. So could I say with 95% certainty that the true average is above 5? Well, if I looked at 5.2, it would suggest to me that the mean for the entire group, 10,000 kids, the average entire 10,000 kids is above 5. Look, the average was 5.2 for the 10 kids we tested. However, the true population mean may not be 5.2. We're 95% sure it's between 3.9 and 6.1, right? So we can't really say with 95% certainty that the average kid in the Bronx is above 5. Now, had my confidence interval been 5.1 to 6.0, then you could say with 95% certainty, the true mean is between those two numbers. So with 95% certainty, you could say it's bigger than 5, right? See the difference? See how confidence interval can help us understand, how well we know where we stand with an average, that the single average they give us as the result of the sample. Now, we don't really use it that way. We don't functionally use the confidence interval that way. We're going to learn about the t-test, where we kind of do something similar to the confidence interval. We look for differences between means of 2 standard deviations or more to judge whether or not we can be confident about the difference between them, right? But at least this gives us a measure of, when you give me a number as an average, when you read, now for instance, if you would go read a study now on blood lead levels in children, if they might take a population of children and say the average was 7.3 and confidence interval was 4 to 10, right? Now, if they just put 7.3, you don't know how precise they know that. Now, because you have the confidence interval, you have a more information about how well you know what the level is for these children, right? You have a better understanding of what the variability is, right? So almost all studies, if they give you an average, they're going to also accompany within parentheses a confidence interval.
Question.
Yes.
On that one, how come you said that 5.2 is not 95% confidence interval, but you said 5 is, if 5 isn't in that range?
5 is not in this range. We're 95% sure the true mean is between these two numbers. right? So that also means we're 95% sure that it's above 5, right? So if we're 95% sure the true mean, mu,
Right,
the true mean is between 5.1 and 6.1,
right.
that also means that we know that it's greater than 5 or greater than 4 or greater than 2, right? But if the true mean, we can't say that it's greater than 5.2, 5.3, right? Because it could be, in our confidence interval, it could be 5.3 and within that range. So we can only say that we're 95% sure it's different if it's outside of that range, right? Either above that range or under that range. Feel a little bit more comfortable with that? Still having trouble with it, I can tell.
I'm just,
Oh, let me put it this way.
yes,
Okay. If I asked you to guess my age, right?
I'm not gonna do that.
Okay, you don't have to do that. You don't have, I'm not going to force you to do that. Okay.
Okay.
So you can guess a number. You could say, Tony, you look like you're 40, right? Okay. If you want a good grade, you're 40. So at any rate, so you're 40. You can guess at a specific number, right? But that's kind of a crapshoot. You really don't. It's not very. It would be very difficult for you to get exactly right. Instead, you could give me a range. Tony, I think you're between 40 and 50, right? So that range now gives you more likelihood of being right. So let's say that you were 95% sure that I'm between 40 and 50, right? That also means that you're 95% sure that I'm not 38,
Right.
right? Because I'm outside,
Right,
right?
exactly.
And where you're not also means you're 95% sure that I'm not 55, right? But you're not 95% sure that I'm not 46, because 46 is in that range, right? Exactly. So in order for you to be 95% sure that it's different from that range, it has to be outside of that range.
Thank you. Now I-
Okay,
So I
good.
need it until you-
Yes.
What?
In that perspective.
Yeah, that
was
helped
Yeah,
me.
here.
yeah.
Okay.
Okay, yes.
Thank you.
But how do you know the age of, say, the security guard?
Yeah.
By knowing your age.
You don't.
So how do you know? I thought, so,
So really, we're not going to use it for an individual person. We're using it for an average. We're trying to predict what the average for a population is.
right, so, but if you, like 30 people, but the whole population is like infinite, like number of people. Oh, not infinite number of people.
Yeah, but it does have an average, no matter how big it is, even the whole population in the United States, 300 million people, there is an average age for the people in the United States. That's a number. It's not a number we're ever going to know, right? Okay, but there is an average. I'm never going to be able to ask everybody their age, right? For instance. However, I can take a sample of 100 people, 1,000 people, whatever I have the resources for, and find the average of those 1,000 people. Well, now I find the average of those 1,000 people is 37 years old, right? And I say, is that the average age of the entire population in the United States? I don't know. Could be just, I got luck. It could be I underestimated him. Could be I overestimated him. Depends on my sample. Bigger the sample, the more confident and more certain you are that you're pretty close to more likely you are to be close to the actual age. But you can't depend on that actually being. In fact, it's almost impossible for a sample like that to be the actual exact average age.
Last week you said.
Just have to have the ridiculous amount of luck. Yes.
Last week you said, if you're doing a study on something and you want to know how many people you want to sample in order to get a good number, to get an accurate number, but you don't know how much.
Right.
I don't.
Oh,
understand
okay.
how
Sample
you get
size, determining sample size. We'll get to that next week. Because sample size is going to be important to us when we start to do studies. When we start to do studies, sample size is important. Yeah, I want to get to that next week. Sample size is definitely important to us because you can do a study. If you want to do a study, you have to have some reasonable judgment. If I want to prove something, how many people do I have to sample to prove it? Do I got to sample 10, 100, 1,000? In other words, you don't want to sample 1,000 if you only need 100, right? Because all the resources and money that go into it. Okay, so that's the idea here. Now, if I asked you, you want to be 95% sure you get my age, and you have a confidence interval that you say you're 95% sure, 40 and 50. What if you want to be 99% sure? What do you do with that range? Make it, if you make it narrower, that makes you more certain.
Right,
Make it
right.
wider.
Yes, right.
Make it wider, if you make your confidence interval wider, you're more certain that the population, that the average that you want or the number you want is going to be in there. If you are willing to be less certain, you can make it narrower. Okay, so let's take a look at where that takes us. Okay, that's a whole new ball game now. Oh, my battery's running down. Let me erase this. See, I got overconfident. I was using a machine that always constantly had to be plugged in. And now I have this one. The battery is great in it, except I forgot my charger now. So I can move over to that machine. I'll be a little bit hamstrung in terms of this, but that's okay. It's okay. My tablet's not working right anyway. Okay, so anyway, so now one thing I want to point out about this. I probably brought this up last week, but when I want to find the confidence interval, I take my average plus or minus, I said 2, times my standard deviation, right, which is based on sigma over the square root of n. What's that? Yeah, to calculate confidence interval. I take the average, which plus or minus, which is 77 before, plus or minus 2 times the standard deviation, right? Which is the standard deviation for the sample means is equal to standard deviation of sample means is equal to sigma, the population standard deviation over the square root of n. Right? So now I'm looking at this, I'm saying to myself, gee, okay, that looks very interesting, but that 2 bothers me, right? Why does that 2 bother me? Because that 2 is not, that's from the empirical formula, right? 2 standard deviation. That's not completely accurate. What number really should be in there? I think we mentioned that last week, right? It was 1.96, because if you go to the Z table, the area, the Z score that gives you exactly 2.5% at the bottom and 2.5% at the top in the tails and 95% in the middle is 1.96 instead. So instead of 2, we put 1.96 times our standard deviation. And you know, the other thing is that this term standard deviation, we use it for the samples, we use it, you know, it's kind of, we don't want to mix this up with something else. That's the standard deviation of the repeated sample means. We're going to give that a special name. We're going to call that the standard error, right? Instead of the standard deviation. Now, this number that we're adding and subtracting from X, we're going to give that another name. We're going to call that the margin of error. And that makes sense, right? Because you're saying, oh, it's 80 plus or minus this. Sounds like a margin of error, right? So that range is defined as the margin of error. So that determines what your confidence interval is. So if I were now to tell you, well, let me do a couple of examples here.
Is that a 1.965?
No, just 1.96 is good enough. So, however, I'm glad you brought that. No, I can't really do this because I'm using this trackpad to do this. X plus or minus, I have this beautiful graphics tablet, but the thing is that it's funky. I got to reboot to make it work right, and I can't do that. So now that's a 95% confidence interval, right?
You're doing great.
Okay, so now if I want to be more certain that I capture the true population mean, I want to be 99% certain. How do I do that? Well, this number that I add and subtract has to be bigger. And it's bigger because in order to have 0.5% in one tail and 0.5% in the other tail, 99% in between, I have to use 2.58. Okay, you might remember that number, times my standard error, right? In order to be 99% confidence interval. Okay, so what if I want to be, I'm willing to be only 90% certain, 90% confidence interval. Well, in that case, we would use plus or minus 1.64 times the standard error. And again, that comes from the Z table, right? The Z table tells us that in order to have 5% in the left tail and 5% in the right tail, so that 90% is in the middle, right? That has to be a Z score of negative 1.64 and positive 1.64. And that's where this stuff comes from. Now, just very quickly, we can also do this with proportions. If I told you that we took a survey of people who eat a lot of cereal, and we asked them, do you prefer bananas to other fruit on your cereal? How many of you eat bananas with your cereal? Okay, let's say we found out strawberries, maybe. Okay. So let's say you survey 1,000 people, and 300 of those people say, oh man, I can't eat cereal without bananas. I like my cereal with bananas. What proportion of these people eat the cereal with bananas? The proportion is equal to 30%, 0.30, right? Now, if I asked everybody in the United States whether or not they like bananas in their cereal, it might not come out 30 the way our sample did, sample of 1,000 people, right? But really what I'm interested in is what everybody, if I'm, General Foods or something like that, I want to know what percentage of people in the country. But I can only sample 1,000 people. I call them up on the phone and do a survey, right? So my sample size is 1,000. 300 out of the 1,000 say they like bananas. 700 of them say they like strawberries on their cereal, right? So the percentage like bananas is 30%. But that's of my sample. My true population proportion, I don't know. I'm never going to know for sure. So I have to do the best I can with what I know from my sample. So instead of calling, I'm going to use P, just like before, where I use mu for the population mean and X bar for the sample mean. I'm going to use P for my population mean. I'm going to put a little cap on top of my P to show us a proportion of a sample. Right? That means now that 30% is not the population, came from a sample. So now I got to do the same thing. In order to develop a confidence interval, I have to say my confidence interval is going to be P cap plus or minus 1.96 times my standard error. Okay, so in this case, it's going to be 0.30 plus or minus 1.96 times, well, now what's my standard error going to be, right? How do I calculate that? Well, in this case, the way we calculate our standard error for this kind of calculation is the standard error is going to, for proportion, standard error is the square root of P times 1 minus P over N. So in our case, it's going to be equal to the square root of 0.3 times 0.7 over 1,000. Okay, I'm going to give that a try down here. Oh, that's nasty. I'll do it over here. Okay, let's see what I got here. Okay, so 0.3 times 0.7 is equal to this. And I'm going to divide that by N. Oops, oh crap. I hit the, excuse me. Like I said, I'm getting used to this thing. 0.3 times 0.7 divided by, I turn my screen brightness down. Divided by 1,000 is equal to that. And I'm going to take the square root of that. And that's equal to 0.0144. Now, I'm going to call that 0.15, just for the hell of it. That's 0.015. So, yes.
And I know you were at the beginning of this page. Where to get the 1.96 from? Why is it that?
Because remember, that's what represents 95% of the outcomes. That's two standard deviations both there. It's 1.96 because we're being more precise now. Okay, so this is going to be what I 0.015. Oh, is it 0.015, 1.5%. So we have 30 plus 1.96 times 0.015. I'm going to just make believe that's 2 to make things simple. So 0.30, you'd actually do it with the right numbers. Plus or minus 2 times 1.5% is 0.03. right? So my confidence interval is going to be 0.27 to 0.33. So in this circumstance, I am 95% certain that the true proportion in the entire population of people that like bananas on their cereal is between 0.27 and 0.33. So I might report my result was 0.30, but my 95% confidence interval for the true population proportion is 27% to 33%, right? See, it educates us about how close we are to the true population mean when we have that value.
Professor, the formula is P times 1 minus P?
P times 1 minus P over N,
Right.
square root of the whole thing, everything that's inside there. So that works out pretty well, right? So we have a mechanism for doing this for proportions as well as for averages. Okay, where are they doing this right now? You're seeing them every day, constantly in polls. Exactly, this is how they do polls, right? Polls are proportion. What percent of people want this guy? What percent of people want this guy, and so on and so forth. And what's the accuracy of the poll? Plus or minus, that's your